Right, well, I think we will make a start. Thank you all for coming along to this session. It's the second one in the series of our coaching talks, and this is one is going to be on instruments and electronic awareness. What we'll cover today are the types of instruments, some of the primary flight data that we use on our flight decks. We'll look at airspace. We'll look at loading tasks and waypoints onto instruments, electronic conspicuity, tracking, and then open it up to a Q&A. So instruments, it's a bit like driving a car, really. They provide useful information, but you really still need to be concentrating on the world around you. Yes, there's a lot more data-rich information coming from our instruments compared to driving a car, but it's still a fairly good analogy. This is not a position you ever want to be in, this close to another pilot. And this actually occurred in Beer last year, in October, about half an hour after I left the house thermal. And I think what you can say here is we had two pilots that had lost situational awareness. Fortunately, they both landed safely, and I think the only problem was damage to the red canopy of the pilot that had the camera. As soon as you start flying on your own, as soon as you come out of the school, you don't need to start tooling up with loads of instruments. You can spend 10 hours, 20 hours, maybe even more, just flying around, enjoying the newfound freedom that you've had outside of the school, and focus really on building a strong foundation of basic skills. But at some point, if you have aspirations to fly across country, it's a good idea to get a Vario. Varios start off relatively cheap, about 40 or 50 pounds, and they can go right the way up to something like the XC Tracer Max 3, which is about 750 pounds. It's one of the top of the range Varios. And they really split them into two groups. The first series are barometric pressure sensors on the top row, and then as they get more sophisticated, they include other sensors like accelerometers and gyroscopes. And that enables the instruments to be a lot more accurate and a lot more sensitive. They also sometimes come with file logs to record your flight, and some of the more advanced versions have FLARM and FANET, which is to make you more visible to other users in the air. The advantage of starter Varos is that they're cheap and they're very simple to use. They've got a couple of drawbacks. There's a lag in the feedback, and they may actually react to gusts and tell you that there's lift when there actually isn't any lift at all, and they generally won't do any flight recording. And so the implications are that at times you'll need to ignore the Vario and instead just relate its feedback to what you feel in the air. And the trouble with that is, as you then move to more advanced Varios and instruments later on in your flying career, you'll need to adjust really how you've learnt to react to the instrument. And it's really a catch-22 situation, because when you first start to fly in thermic air, you don't really know quite what's happening, and you want the instrument to be able to be a bit like a teacher and to help you feel what the air is doing and tell you that you're in rising air. And eventually you can become much more adept at understanding the feeling in the air around you and the fact that you're going up. So that's one of the major drawbacks. As you move to more advanced instruments, you're going to have to change the way you react. The more advanced Varios, they have this sense of fusion, so it provides a lot more immediate feedback. The feedback is much more closer to reality. It records the flights. It sometimes might display additional flight information, and it may include FLARM and FANET, electronic conspicuity features. The only drawback really is they're expensive. And the benefit there is that when you don't have to compensate for lags and inaccuracy of the instrument, and you can continue to use that as you go through your flying career. The most important thing when you start off flying with Vario is to set it up correctly. So this is the polar curve. So it shows airspeed on the top on the x-axis, which in still air your airspeed will be equal to your ground speed. And so the airspeed there is really reacting to how you move your brakes. And then we've got sync on the y-axis, on the vertical axis. And so there's your optimum glide. And In still air, you're going to be sinking at about 1 meter a second. When you're actually soaring along a ridge, your sink rate is 0. So you're actually in rising air at 1 meter a second. So that's a good thing. So you really need to set the lift threshold on your Vario to as close to 0 as you can get it. So maybe 0.1 meter a second if the Vario won't actually accept a 0, 10 centimeters a second. And then in terms of sink, you want to set the sink threshold to something around minus 2 meters a second or 200 centimeters a second. So that when you actually get into sink and you're lower down on the polar curve, that you now know that in order to get optimum glide in sync, you need to go into speed bar. So you don't want your Vario going off all the time. You just want it to go off basically when it's telling you to do something. So if you set the Vario up with those settings, it's going to tell you to either turn in lift or use the speed bar in sync. And this is just trying to demonstrate that if you set your Vario to only trigger at, say, 1 meter a second, or 1.5, this is trying to show a representation of a thermal. So you get a high climb rate at the front of the thermal. From further downwind, you get a much lower thermic rise in the air. And you can actually fly straight through that, certainly when you start flying and you're a bit inexperienced and you don't really know what to expect. You can actually fly straight through this air, which is rising at 1 meter a second. Your thermal wouldn't indicate it. So by having it set to 0.1, at least it's going to tell you that something is happening around you. Experienced pilots can detect thermals through very subtle changes through the harness pressure, through the wing feedback, the wing movement, and sometimes even acceleration as it takes you through into the thermal. And one of the very experienced pilots in our club was doing a flight in France, in the French Alps a few years ago, and his Vario packed up, and he continued flying for at least another 50k just by feel. Alternatively, you can use phones, and it doesn't matter whether you've got an Android phone or an iPhone. There's two very good bits of software, Track and Fly Sky High on an iPhone. That's a very powerful flight instrument, lots of functionality. And the real advantage of phones is no additional cost. You already own one. The apps are free. Well, Track is free out. I think Fly Sky High might be a nominal initial fee. The coloured screens are very good. They improve readability of terrain, airspace and navigation. And you can customise the display to be whatever you want. But they've got a number of disadvantages. The first one is screen visibility can be really poor in bright sunlight. The sensors inside them are less accurate than dedicated flight instruments. If you have the screen on full brightness, you're going to use up a lot of power, so you probably end up going to have a power bank. Screen sizes can be small, although the phones are actually getting quite large nowadays. And they can certainly overheat in very strong sunlight, particularly if you're using the internal GPS of the phone. Another major drawback is the risk of total loss. If you land badly and damage the phone, you've lost everything. You've lost all your comms via WhatsApp. You may have ground navigation stuff on your phone. You can't phone anybody. So you potentially could be in quite a serious situation if you damage the instrument as you land. And the other thing to note is not all phones have a barometric pressure sensor. Some of them, even the expensive phones, don't have one. So you'll be relying solely on GPS altitude. For new pilots, they're excellent, but they're not ideal as a sole instrument for XC flying. So in practice, most people use a phone alongside a dedicated Vario that you can either connect up with a cable or via Bluetooth to your phone to get some accurate data going into the phone. The other alternative is you use the phone only for map displays, navigation, airspace awareness, while you use a dedicated instrument with the more accurate flight data. And a lot of really experienced pilots will do that. In competition pilots as well, they'll have a very good dedicated instrument, but they'll still have a phone next to it for mapping and stuff. And there is a massive variety of instruments out there. This just gives a very small selection. The Cyride XL on the top left, about about £400, going right up to Flymaster Live, which is well over £1,000. The Skytrax is quite popular. You see a lot of those around. The Skytrax 2.1 with the orange casing. A lot of them are grey with the black text, which makes it very easy to read in flight. It's interesting to see that some of them are now going to have colour displays, And the Flymaster Live has got colour display and the traditional display next to it, which is quite a nice combo. And it's systems like the Syrah Evo V2 is now going for larger screens. Surprisingly, some of these instruments have got quite small screens, only 3.5 inches, which compared to today's smartphones is very small. And all the top-end instruments will have Fanet and Flam on them as well. They're accurate, they're sensitive, they've got all the advanced navigation tools on there. You can get all the airspace maps on there. It will log your flights. Normally they're quite easy to read in bright sunlight. You've got all the connectivity with all the other instruments, and Flam and Fanet and Wi-Fi connections and stuff. You can customize the displays, and they're obviously very good quality. A couple of drawbacks: they're high cost. You've got quite a steep learning curve. Small screen on some of the instruments, and the airspace can be quite tricky to set up on some of the instruments. But if you're going to do a lot of XC flying, they are definitely worth it. So we're now going to look at a bit more detail at the primary flight data which you need to have on your instruments. So we've got the 3 altitudes: flight level, Barra altitude, and GPS altitude. We've got ground speed, altitude above ground level, and we've got wind speed and direction. So this is taken from the Skyway code, and it nicely shows the 3 altitudes that we fly at. We've got altitude, we've got flight level, and we've got height. And the only thing that's different between the 3 of them is the reference pressure that they use. So with QNH altitude, you're basically setting the pressure at sea level to whatever it is on the day. And that's referred to as a QNH. They're old-fashioned Q codes that they used to use in the days of Morse code. Those letters don't mean anything, but you can try and remember it if you want to by N being nautical, which is a C. And for QFE, F for field and ground. Flight level is basically reference to a standard pressure of 1013 hectopascals. And then height, which is height above the ground, AGL, is reference to takeoff. And as such, we don't use QFV as paragliders. For skydivers, we would set out altimeters to 0 when we take off, so we know where the ground is when we're coming down in free fall. But as such, we don't set our instruments to the pressure at takeoff. Flight level is, as I said, is set to a standard pressure. And here it's indicated flight level of 3.5. You either multiply by 100 to get it into feet, which is 3,500. Or I tend to just divide it by 10. So flight level 35 is 3.5 grand. And on your flight level here is 3,500 feet, which is, it will be indicated at 3,500 feet, even though you're exactly the same level as a pilot flying on QNH. And the reason is that it's referencing the pressure at 1013. If you were to fly on a high pressure day to flight level 40, it's indicated at 4,000 feet, it would be much higher than the pilot that's flying on a QNH at 4,000 feet. So a flight level of 40 is physically higher than a pilot flying at 4,000 feet on QNH on a high pressure day. And you may sometimes hear experienced pilots say that if you fly to the flight level in feet on a high pressure day, you're always going to be below the ceiling of the airspace. So if you do not have QNH altitude or flight level on your instrument on a high pressure day, if the airspace is at flight level 40, you can fly at 4,000 feet GPS altitude and you will be below the airspace. So flight levels are pressure levels expressed as altitude using a standard pressure setting of 1013 hectopascals. So if you were to take 2 aircraft in different parts of the world, an aircraft A departs on a low pressure day and flies at flight level 350, it will be flying lower than it would in a standard atmosphere. If another aircraft B departs on a high pressure day and flies at flight level 350, it will be flying higher than it would in a standard atmosphere. However, if both those 2 aircraft are in the same airspace where the surrounding pressure is the same, then Flight level 350 represents the same pressure surface, so both aircraft will be at the same physical level, effectively the same true altitude. So in order to avoid collisions, aircraft operate at different flight levels, for example 350, 35,000 feet, and 360, 36,000 feet. And by doing so, when those two aircraft meet in the same airspace, they will be at a flight level difference of 10, which is 1,000 feet difference, and therefore avoid a collision. And here are the numbers that have been used to calculate the pressures. Now, we said the change in pressure there is 1 hectopascal for every 27 feet. In practice, it changes with altitude. So you need a change of about 40 feet to get a change of 1 hectopascal at 15,000 feet. And there's two sources of QNH pressure. You can do it via METARs, which is airports and aviation services, or you can do it by information service at larger aerodromes. And those will supply for any given day what the QNH pressure is, which you would need to put into your instrument. And certainly within XCTrack, you've got two settings you can use, standard or QNH. So we would set it to QNH, and so long as your instrument is connected to the internet onto mobile data on the morning that you take off, the pressure will automatically be transferred into your instrument. Otherwise, you've got to go online, get it online and put it in manually. And that will give you your QNH altitude then for the rest of your flight. Having got your QNH pressure, P0 in there, there's a formula that's used in the instruments. So for your ambient pressure, it calculates your height above mean sea level. Interestingly, you can also use this equation if you were to put the reference pressure in at 1,013 hectopascals, and the height you would get then would be the flight level. The other way of doing it is to use international standard atmosphere tables, which gas turbines in the aviation industry use. In terms of GPS-derived flight data, GPS, and it measures the time from various signals that go between the satellite, and it calculates your latitude and longitude, but it doesn't actually know your height at the start. So there's an ellipsoid model, the WGS84 ellipsoid model in your instrument that's an approximation to the surface of the Earth. Ellipsoid sounds like a squash potato, but it has errors in it. So if you're flying in India, it could indicate you were flying 100 meters lower than you actually were relative to mean sea level. So there's an additional correction, EGM 96 correction for height above sea level, and combining those two, you get a far more accurate representation of your height above mean sea level. In order to calculate AGL above the ground level, it needs a terrain model. So within your instruments, you've not only got ellipsoid and rotational corrections, EGM 96, but you've also got a terrain model in there, puts in there an estimate of the terrain, and then gives you your AGL. It also has ground speed and direction that you're traveling in. Thing to be aware of is, because of potential errors in all of these models, close to mountain terrain, you could have an error in the instrument by plus or minus 200 meters. So what you'll find is some instruments actually use a much more accurate QNH value of altitude, because you've calibrated everything out before you take off by setting it to the pressure at sea level on the day. And then it's just a simple relationship between the pressure you measure and the altitude. This is showing wind direction using a digital compass. I think most instruments are similar. So what you've got, the GPS data will tell you the wind speed, and it will tell you the wind direction. But you've also got a digital compass, and the way that these digital compasses work, and there's a number of ways of setting it up in XCTrack, but probably the best way is to set it up, as I've shown on the left-hand side there. So the heading is always at the top. So wherever you turn, this stays at the top of the screen because it's assumed you're reading the instrument in front of you. If you were to take your instrument and turn it upside down, this little white marker would now be at the bottom of the screen. It assumes you're going backwards. So your heading always stays at the top of the screen. And what happens is this compass rotates, and it to such extent that it's showing you your flight direction. So this was taken at Fokru, and I'm flying, there is north is up here. I'm flying roughly southwesterly. And if you look at the instrument, north, south, east, west, that's southwest. That point there is southwest on that compass. The wind's also coming from the northwest. And if you look at this compass, that is the wind direction here. And that's north, south, east, and west. So that's northwest. Well, what you're going to bear in mind is this true north. This is effectively showing you that if you wanted to fly north, you would have to turn through that angle. This just shows you another example. So that I'm flying just a little bit west of north, and the wind is now coming from the west. And so look at this digital compass. There's my direction, my heading, and the north is just a little bit to the right hand side of me, to the east of me. The other thing to bear in mind is that heading and bearing can be different. So your heading is this white arrow, but you could be tracking along the ground because of the wind. At some stage in your flying career, you're probably going to end up in the white room. It could be because of cloud coming over the mountains in places like India or Colombia, but it could equally be flying at some of our local sites due to orographic cloud, either at Rossilli or even Hay Bluff. I've seen it happen at Hay Bluff. And something that's really good to do is always know what your safe heading is before you need to use it. So if you're flying at, say, Rossilli, you know that the safe heading is west. And so if the worst case happens, you don't have to think about where you are on the map and which direction you need to fly. You know that the safe route out is to fly west. So if you are flying with that, you can either look at your digital compass, that's your heading. You know you'd need to turn through about 90 degrees to the right in order to hit the north. The other way of doing it is just look at the compass, and wherever north is, that's the direction you need to head in. When you buy a compass, you've also got to be aware that there's two types of compasses you can buy, the classic compass and a boat compass. You turn the boat onto the heading you want by looking at the position closer to you. So when you see north on the dial that's closer to you, then that's north, even though at the top of the compass it's saying south. So in both cases, north is in the upward direction. In one case, you would look at this compass here, the ball compass, and head in that direction. In the other case, you'll be looking here. If you've actually spent your life in the wild navigating with a map and compass, and you're used to going from field to map and map to field using a magnetic compass, it's probably advisable to get the classic compass type. But if you haven't done a lot of map work outside, maybe you could just get a boat compass. But I think for most people, it's probably best to get a classic compass. As far as indicator wind speed is concerned from your GPS, it's very much influenced by the strength of the thermal. Because in a strong thermal, the thermal tends to block the wind to a large extent. So as you're turning the thermal, you're not drifting so much. As the thermal gets weaker, it bends over more with the wind. So the thermal drift is more. So the wind speed is a bit more accurate. And do 360-degree turns outside of a thermal, then you get a lot of drift and it will show you the wind speed more accurately. In practice, you're not going to start turning outside of a thermal. So just got to bear in mind that the wind speed is indicated on your GPS instrument. If you're in a thermal, it's going to be lower than your actual wind speed. The other way of doing it, and the most normal way of doing it, is when you're flying downwind at trim speed, the ground speed minus your trim speed 37 will tell you the wind speed. You can also obviously determine it by flying into wind as well. In terms of wind direction, although you're not drifting very much in a strong thermal, you are still drifting with the wind. So wind direction is generally more reliable, even in a thermal. So I'd just like to ask you a question on a poll. If you're flying as a bluff, and on one leg you're doing 47, and on the other leg you're doing 27 kilometers an hour, what is the wind speed component along the ridge? So most of you have said that it's 10 kilometers an hour. So it was actually 10 kilometers an hour. So all you have to do is take 47 minus 27. So the two beats away from each other and divide by 2. If you know the trim speed, and it's more normal to do this, if you know the trim speed of the glider, it's simply whatever your ground speed is minus the trim speed is going to give you the wind speed. And obviously if it's positive, it's behind you. If it's negative, you're flying into wind. 27k ground speed minus your trim speed is 10. One of the things you want to be quite careful of even when you're soaring is a change in wind direction and the impact that it might have on turbulence. And this is Milk Hill White Horse over Alton Barnes. The wind normally comes straight up the slope, but in this particular case, there was an incident a couple of years ago where the wind backed southeast, and there was quite an experienced pilot had a nasty accident here. They hit turbulence at 20 meters off the ground and hit the ground. Fortunately, they survived, but they had some nasty injuries. So always try and monitor the speed, your ground speed on the beats, which would indicate that the wind has changed off the hill, and see whether there's any terrain around you that could cause turbulence. Some good examples are, say, the Pandy Ridge. If you're low on the Pandy Ridge and you're trying to do a transition, particularly from the start, from takeoff up past its first spur, if the wind is now starting to come off the hill and more around to the north, you've got to be really careful of any turbulence coming off there. If you're high enough, it doesn't matter. In fact, if you're high enough, you might even get a thermal. But if you're low, you could be very careful about hitting turbulence at various places along the ridge. Another area is at Hay Bluff. When you want to go in your first cross country, you need to get a thermal normally about 1,000 foot above takeoff in order to transition over to Tumpa and carry on flying ridge soaring along this ridge. But if you actually start doing this too low and the wind started to come off, you can equally get turbulence here. So it's something to be very cautious of. In the mountains, the wind that could cause these problems isn't just meteor. It could be the valley wind, it could be thermal flows, or it could be a combination of them. So what's quite useful to do is when you're flying at trim speed, look at your ground speed. And if your ground speed is greater than trim speed, you'll know you're flying downwind. And if your ground speed is less than trim speed, you're going into wind. So if you're ridge hopping from one ridge to another, you know whether you're going into wind or downwind. If you're going into wind, you've got to be very careful about possible turbulence. And if you're flying downwind, it's safer in that sense. And you could even use a ridge, if you get there low, you could even use a ridge when you reach it to start to do a bit of soaring to get further up. When I did my coaching course, the BHPA senior technical officer said that one of the common reasons for newer pilots having incidences when they're soaring is due to this. So I'd just like to briefly go through it. We all know that if the wind's behind you, go faster, and if the wind's in front of you, go slower. We all know that pulling brakes down makes your ground speed slower. But the issue is the brakes also control airspeed, and it's the only thing that controls airspeed. So if you pull the brakes down sufficiently, you will stall the wing. Even though your ground speed might still be quite high in a tailwind, you could stall the wing. And the scenario that was cited at the coaching event was slowing down on a fast beat. So the wind is slightly off the hill. You're doing a soaring beat. You're going very fast. And before you turn around, you want to slow down. So you pull the brakes to slow down, and then you hit the outside brake to do a 180-degree turn back. And at that point, you are going to spin the wing. Another scenario is approaching a landing area. You're going very fast, for example, maybe you're going downwind, and you apply the brakes, and then you want to turn around to face into wind. And you do that quite sharply from a fairly brake position. Again, you can spin the wing. Another potential cause could be when you start soaring later on, you might do a bit catch a few thermals and be a bit further out from the ridge and quite high. You may then decide you want to head back to the ridge because you come out the thermal. So you'll start heading downwind back towards a ridge and be going very fast. So you'll apply brakes to slow you down, and then you turn, say, left in order to get parallel to the ridge. And that's another situation where in doing so, you could spin the wing. So this is how airspeed is calculated. on your GPS instruments, it takes your ground speed, which you're going downwind would be quite high, and it takes off the wind. So this would give you an airspeed of 40. If you're going into a headwind, your ground speed's going to be quite low. And I had on the same wind strength, 25, to get 40. Another thing that's quite interesting is if you add on the ground speed on both beats and divide by 2, you get your airspeed. But as we've just done, if you take off the ground speed on one beat from the other ground speed and divide by 2, you get your wind speed. So the main takeaway from that is if you've got a strong wind behind you, provided your ground speed stays fairly high, you are safe in terms of airspeed. The danger is always trying to reduce your ground speed with a strong tailwind, which reduces your airspeed too much. So this is the instrument I fly with, and this is the first screen I've got. The important information should be displayed in large text at the top of the screen. This XC distance widget is really quite cool. I used to think that once you've done a flight, you'd have to upload your track log to either X-Contest or XC League to see how far you've flown. Certainly on XC Track, on Android phone, I'm sure iPhones are the same. You can go into your track logs and just look at your routes, and it will tell you immediately how far you've flown, and whether it's been a turn point flight, which is putting 3 points through your flight between landing and takeoff. If you've done a triangle, it will tell you your triangular distance. But you don't even need to do that. In flight, this XC distance will give you that same information before you've landed. If you say you've done 48 and 49 kilometre flight, and it's your first 50k flight, it's very useful information to know that instead of landing in the field one side of the road, you can just land in the field the other side or 2 fields down, and you'll have done 50k. It'd be rather annoying to land on your first long flight and to find it was only 49k. The other things I have at the bottom here are a Vario on-off switch, and also airtime and my vertical speed. The vertical speed I use here, I average over 7 seconds. Different pilots have different views, but you really want your speed averaged over a reasonable amount of time to tell you which side of the thermal is the most effective at giving you lift. You can look at on the same map. There's lots of, I've just zoomed out here to show all the airspaces that are there, and you can download the airspaces and the NOTAMs reminders onto your instrument on the morning of the flight. My second screen is an XC map and airspace proximity. So the XC map gives you some idea what you're flying over, and it might give you some ideas about where you might want to land on a long XC flight. But there's a really cool widget called the airspace proximity widget, and the other instruments have got it as well, because I used to think you'd have to look at the airspace in front of you on the map, then look at your altitude, figure out how much clearance you had from the airspace. But this widget does it all for you. If there's more than one airspace surrounding you, it tells you what the airspace is. It tells you how much height you've got to go up before you hit it, and how much distance you've got to fly laterally before you go into it. So in this left-hand image, you're 5,000 foot below the airspace, but you're actually inside it by 780 meters. And the other great thing about it, these instruments, they'll fire up messages when you get close to airspace, like you are close to airspace. Then it will say you are very close to airspace. Then it might even sound an alarm. But if you look at this widget, it also changes color to orange and eventually to this purpley color when you're actually in airspace. So you've got a lot of indications when you go cross country that you've got airspace around you, and your planning should cover that as well. So this is a demo that I did in a car with XC Track, and it shows the airspace proximity and side view widget, and it indicates the terrain profile and the airspace that's in front of you. So you can see as I've got closer to the danger zone, colors on the airspace proximity change. The third screen I have is a thermal assistance screen. It's got a Vario bar here. You can set it up so the thermal assistant page comes up as soon as you've done a turn in the thermal and disappears again when you come out the thermal. It also tries to indicate the core of the thermal. I haven't tended to use it a lot so far, but it's more useful in flatland flying than in mountainous terrain where the thermals are affected more by the terrain. And some instruments have got very, very sophisticated thermal assistance. Another thing you can have on your instrument is a thermal overlay, which it looks pretty good. It's telling you where thermals have previously formed it might help you in flight. In practice, if you're in a situation like this, I'm not really looking at my lovely thermal marker that's in front of me on my screen. In busy airspace, I'm really having a look, see what's around me and see what I might have to do to deconflict with another pilot. I'm also looking for visual clues like other wings going higher than me above the horizon, birds going around in circles. I'm looking at the terrain to see where the thermals might trigger. This is a particular example of San Andreas, where there's an area of very broken rock down here, which creates thermals, but then it can be quite a turbulent area. And also, if there's clouds around, you're looking at clouds. So looking at what's around you is far more important than looking at a thermal marker on a map. And if you're flying along a valley and it says the thermals are going to be on the left-hand side, if that side of the valley is in shade and there's no clouds above it, there's no birds moving above it, I'd probably go to the sunny side, regardless of what the thermal tracker on my instrument said. It's also worth saying that you don't have to wait until your first cross-country flight to fly your first task. Like many things related to cross-country, you can practice on the ridge beforehand. So with instruments, you can actually set up a small task. It could be just 2 points, one at either end of the ridge, 2 points on either end of the ridge and the landing area. And you can fly that task and just see how the whole system works. Clearly, you would need to make sure that you're in fairly clear airspace and relatively high before you start looking at your instruments. But you can actually fly a planned flight on the ridge and get through to goal, which is quite satisfying. It may be quite a long time in the flying career before you actually get to goal. This was a flight on that magic day last year, 3rd of July, when Benjamin Dry did an 8-hour flight from our area right across Middle England. If you fly from Magic up to North Wales, you hardly pass any airspace. But if you fly through central England, you have an awful lot of airspace to cover. And you can actually set it up. The idea when you do this flight is to try and set your markers, only 1 or 2 you'll need, to try and miss the tricky bits of airspace. So you can see on this post-flight assessment using flyxc.app, there's various bits of airspace that are lower than the others. So you could set your flight planning to try and avoid these airspaces if you can. And I'm not proposing to go through pilot theory on airspace, but this is just an overview of it. There's classes A, C, D, E, and G. A is very high altitude airways that we're not going to be anywhere near. And some terminal maneuvering areas, which we'll talk about in a second, we're not going to be flying in Class C airspace because it's above flight level 195, which is 19,500 feet. Most aerodromes, CTRs, CTAs, and TMAs are Class D. We don't have to worry about Class E airspace, which is in Scotland predominantly, and we fly in open airspace Class G. So the only airspace we really need to be considering are A and D. And there's 4 main types. There's a control zone, the CTR, which always starts from the ground and goes upwards. Then you've got CTAs that start above the ground and go up to another level, and they're areas. And then you've got terminal maneuvering area, so similar sort of thing. It's an area, covers much more busier airfields. And finally, you've got the airways right at the top. You've got military air traffic zones, which strictly speaking are not controlled airspace, but they all have ATZs in them, which are aerodrome traffic zones, which you need to avoid. And they're 2,000 foot from the ground upwards, and their radius is depending on how long the runway is. But these MATZs have no flying in the ATZ, which is in the centre. In theory, you could potentially clip one of these on a weekend when there's no military flying, but generally they're best to be avoided. These stubs that come off the ends start at 1,000 feet above ground level. So while it will say here 1,000 feet to 3,000 feet, you'll find that your instrument converts everything that's above airfield level, above AGL, it converts it to above mean sea level. So on your instrument, you'll see this as 1249 is the lowest altitude it goes down to, and the highest altitude is 3249. So there's your 2,000 foot of airspace thickness, but it quite nicely tells you what it is above mean sea level. So you might think, well, what altitude do I use? Some things like ATZs are not covered by your Airspace widget. So you've got to just look at the map. So in this particular example, it's a flight from Malvern. I'm heading north, and there's airspace in front of me, and it's ground to 2,000 feet. It's an ATZ, but I'm flying at 4,000 feet, so I'm way above it. There's a westerly wind on this day from Malvern, and I'm flying pretty north. So if you look at the GPS compass, my direction is there in the white blob. The compass has rotated, so the direction is north underneath me, and the wind direction on this compass rose is westerly. So most of the time, AGL is not used for airspace. We do have exceptions, the low flying rule, 1,000 foot above crowds, and the 500 foot rule. The only time I tend to use it is, it's not always obvious how high the ground is below you. And if you're on a high plateau, you may end up in a situation where there's no thermals triggering off that plateau. And I've landed a couple of times on the plateau, when really what I should have done was fly to the edge of the plateau, where the thermals are more likely to be triggering. And the way to do that is to look at your altitude, your QNH altitude, and take off your AGL, the altitude above ground level. And that gives you the terrain elevation. So if you know that you're above something that's 800 feet high, and it's not always obvious from the air, then in that situation, if you're trying to find a thermal, you're better off just flying to the side of that high piece of land. So if you're flying at near Cardiff, this is the Cardiff CTR, it goes from the ground right up to flight level 105, up to 10,000 feet. So the only thing you need to know is your flight level. If you're flying near Cardiff CTA, it's down to 4,000 feet above mean sea level and up to flight level 105. So use your Barrow QNH and your flight level. For Cosford ATZ, it's ground to 2272, so all you need to use there is QNH. For this MATZ, Barrow again is all that you required, your altitude above mean sea level, and the Pontrilas danger area close to us here is again QNH. In practice, your widget will tell you how much altitude you've got left. So you could look just straight at QNH for that. Barrow altitude is accurate, but in theory it requires QNH to be updated if you were to fly from one side of the country to another. I suspect the pressure change there would be fairly insignificant, and if your instrument has got data connection to mobile data, it's going to update automatically in flight anyway. GPS altitude is less accurate, but it doesn't require calibration when the weather changes. So there is maybe some advantage if you think you haven't set your QNH properly. In this particular case, you can see my GPS and my Barrow altitude are very similar. XC-Track is the most fabulous instrument to load flight tracks into. Probably one of the most easiest instruments of all of them. And all you have to do is select navigation, load task from, and you can load it from a file that you've created beforehand, or if you're on site and somebody's created a task for you, they can email it to you or just show it to you on your phone. You can scan a QR code. It's a good idea if you're flying your own task, is just to set it from race to elapsed time. So you don't really have to worry about going into the starting gate, the first turn point, at the right time. And if you're flying abroad, you don't have to worry about different time zones on your flight instrument. Because on a real competition, if you fly into the start gate outside of the time, it's not going to trigger the flight starting. The other thing you'll need to do is set up the first turn point so it's away from takeoff. So your instrument detects takeoff, and then you can fly into that first turn point. It'll detect you're inside it, and it will trigger the start of your flight. Waypoints is another way that you can set up a task. You go into the Waypoints navigation area, select this flag, click files, and these are waypoints we had for the competition in the Lake District. And you can just select one of the waypoints, and then you can add other waypoints. So you might have 3 or 4 waypoints. You convert that to a competition task, and you're back to where you were. In reality, if you're free fly, you just fly where the sky and the clouds are telling you where to fly, and the terrain is telling you to fly. It's nice to have a task on your flight instrument, maybe to tell you how far it is to the next turn point. But if you got your XC distance on there, it's going to tell you how far you've flown anyway. So if you say in India you wanted to fly out for 45k and back again, your XC distance widget is going to tell you that you've flown 45k, so you know when to turn back. And then when you're heading back to the start, again, you can figure out how much distance you've flown. Where it starts to becoming really useful is when you're flying cross country through lots of airspace, and you've got to choose a route that's going to keep you out of it beforehand. In competitions, there's a lot more that you need to add to ensure that you get to the start gate on time, etc., etc. You can have things like the wind direction is changed with the altitude on your instruments. There's so much you can have on your instruments if you really weren't in that technical. There's 4 types of waypoint files. The most common is the stock cup file, but they're GPX and WPT files as well. Electronic conspicuity is basically what makes us visible to other aircraft in the sky. And FLARM and FANET are both terms that we've probably heard about. FLARM is a collision warning system which is live, and it's used for paragliders and gliders. And certainly in a glider, it will predict your flight path and give you a warning sign within your cockpit. We don't have it on receivers on paragliders, but sailplanes do. And FANET is used by paragliders and some light aircraft, and it shares position peer-to-peer. In terms of airborne visibility and tracking, there's 4 things we can look at, and it's quite a complicated area, but there's to be seen electronically, the tracking platforms, in-flight tracking apps, and satellite-based tracking and comms. So for to be seen electronically, there's FLARM. It has a typical range of up to 20 kilometers, but quite often in areas that we fly, we get less than that. And it requires a radio module in your instrument, so you don't need an internet connection. And we only transmit, we don't receive like sailplanes. FANET passes the data between instruments from one paraglider to another over radio connection. And you can also have a network of ground stations that will also connect that to the internet. Some instruments have what's called FANET Plus, which just combines the two. And then Safe Sky, it requires an internet connection, but it will send your position back to the internet, combine it with all the other data that's coming in, and send it out to everyone. So a lot of small general aviation aircraft use Safe Sky. So it's a really good route in to get yourself visible on a lot of general aviation aircraft that might not necessarily have FLARM, but you do need to have an internet connection. And the various radio protocols that it has is fantastic. So it'll pick up FLARM, FANET, it'll pick up various other flight instruments, it will pick up your tracking devices, satellite tracking devices, and make you visible to other aircraft in the vicinity if they've got Safe Sky. ADS-B is what a lot of general aviation community use, and it's what the CAA are potentially trying to get everyone to use that flies in airspace. Paragliding community, we're trying to push back on that. The kit's too expensive and heavy for paragliding use. Pilot Aware is another system where in your local area you would have to put a ground station in, but it basically picks up your FLARM and FANET signal, combines it all, and sends it back out to pilots in real time. It might be useful if we had a receiver for more awareness, but it's really quite bulky and it needs a battery. So FANET and FLARM are much better fit for us rather than Pilot Aware. So this is just a summary of the Be Seen element. And the 3 things that we would use is FLARM, FANET, and Safe Sky. Safe Sky is available as an app on your phone that you can use, and it's available within XC-Track. You can just go into XC-Track and switch it on. You'll automatically be included in the Safe Sky network, which is a really good thing to have. Live tracking, massive subject. I've tried to simplify it here by saying there's various types of tracking platforms: Live Track, X-Contest, OGN, Sports Track, Live Gaggle, etc. The drawback of these is you've got to register for each one of them separately, and if you want to be seen on a map, you've got to go into each one of these separately. PureTrack, which we'll talk about in a bit more detail in a second, combines everything into one. Then there's a whole lot of apps to see other people in the sky. So XC-Track, Safe Sky, Sea Navigator, XC-Guide, and then FANET is where we can use it for peer-to-peer with a radio connection in flight. And there's a summary of that. All of them require mobile data. with the exception of the Open Glider network, that has a whole series of ground-based receivers. So you do not need any connection for that. It will pick up your FLARM signal. The other exception is PureTrack, which will receive FLARM data. It will pick up FANET data, and it will pick up satellite tracking data. In-flight tracking apps, they all require mobile data in order to use. And there's loads of other ones like Fly Sky High, Flymaster, Live, Gaggle, Wingman, etc. Loads and loads of in-flight tracking apps. Satellite-based tracking systems, there's Garmin and Spot, but the latest Spot X, has got two-way messaging. I think it's generally considered to be less reliable than Garmin, and Zoleo, not something we tend to use. The Garmin Messenger is compared to the Garmin InReach, is cheaper. They both require subscriptions, but you've got you can link it up to your phone, and it's really cool because you can just type messages into your phone, and it will send it by satellite if there's no signal, and it will send it by 4G, 5G if there is a signal. So it's a very, very useful bit of kit to have. One of the things about Garmin is if you trigger the SOS button, and this happened a couple of years ago in India, in Beer, if you trigger the SOS button, all non-essential messaging and location updates are disabled. So the Garmin uses MapShare. So if somebody was trying to find you on MapShare, once you push the SOS button, you don't appear on the location. Your current location doesn't appear anymore. So that became quite an issue a few years ago in India. But Pure Tracking is becoming the go-to place for tracking. It doesn't matter what source you've got, it will take it in and accept it and display it on a single map as a single map marker. So this is our crew out on the Pandy Ridge. The ideal system is to have 3 independent tracking systems, to have a satellite tracking, to have FLARM or FANET, essentially FLARM, and the OGN network will pick that up via the ground station, and it's using radio for that, and also have live tracking. So X-Contest on XC-Track will give you the live tracking, which requires mobile data. And what PureTrack will do is it'll fuse all 3 data sources together and use the most recent one to put you on the map. So this is a recent flight I had, and InReach was only going off once every 10 minutes. So I only had 14 InReach, but it had 285 OGNs and almost 4,000 live tracking points. So it's really a very, very good thing to register your kit with PureTrack, and PureTrack is free. The other great thing about PureTrack is that in the event that you have a Garmin SOS message, PureTrack pulls a KML feed, that's a live feed from the Garmin's ground servers via network URL. So it grabs hold of the Garmin's satellite data that's gone to ground on their servers, and PureTrack pulls it in and displays it on the PureTrack map. So it's just another really good reason to register with PureTrack. There's lots of competitions now in the UK and abroad are making it mandatory for people to set up a PureTrack account and register their devices. I'd just like to finish on this slide. And the title really says it all. When you don't come back, why satellite tracking matters. Both of these are relatively recent, so they've occurred within my flying career. And one of them occurred in the French Alps. And I remember at the time, the family put out a message on social media urging all pilots to use a reliable tracker. And I think that satellite tracking in both those situations may have enabled faster location, potentially different outcomes to both of those situations, which were obviously very tragic. That finishes the talk. So are there any questions?
Chris, not a question, but just whether you've seen the latest stuff on the Flybrief being put together by Steve Wagner called flybrief.app.
No. What does that...
So he's pulling in NOTAMs and Tim Pengraff's A-Select. It's a really useful tool, both for planning and being able to take a .text file to put in your instrument.
All right, I'll have a look at that. Thank you.
Yeah. It's so he's mainly on the Rutland Telegram site, but a few other people are picking it up around the bazaars. But it's called Flybrief,
Flybrief.app. I'll have a look at that.
Yeah.
Thank you.
I've got a question. I use XE-Track on Android phone, mainly as just a flight log. I just have it in my pocket, just to record the flights. But I've just got the basic setup on it as it comes. I've managed to add in a background map to it, but I'm not really sure how else to set it up. Are there any easy guides on the best way for setting them up?
I think there is a video somewhere on the internet that shows you how to set it up. One of the benefits of Fly Sky High, it's much more intuitive feel to it. XE-Track is less intuitive until you've got used to it. You can go in and basically drag the widgets around that you want to have, put them on the screen. There's one video somewhere online. I'll try and find it and post it on the Telegram group. Once you got used to it, it's actually quite easy and quite flexible. First time you come across XE-Track, it feels very, very clunky, the interface. Well, if there are no more questions, thank you for attending. The next talk we'll be having is on wing control. By far the most important topic in this series of talks. Okay, thank you all. See you on the next one.
Thanks.